Okay, in this video, I'm going to again walk through some more applications of functions. So these are mostly word problems, and I'm not particularly interested in your ability to learn how to answer these questions specifically, but more in general, how do you handle functions and how do you interpret their results in an applied sense. So in this particular scenario, we have Rick Barry, who's a retired basketball player who used to shoot his free throws like a granny shot. Now, I did go out to Google and I found some images of this basketball player. This is Rick Barry here, and you can see that he's throwing the basketball kind of underhanded while standing at the free throw line. So it's assumed, or it was assumed at the time, that when you throw underhanded like this, you're releasing the ball from a lower position. So therefore, the angle of trajectory towards the basketball hoop is going to be much higher. And when the basketball approaches the hoop at a high angle, then it seems like there would be a better shot or better chance of it going in the hoop. So if we think of this little sketch here of a basketball player shooting a shot, if they shot with the ball at their head or above their head, the ball would follow a relatively flat arc towards a hoop that's 10 feet in the air. Whereas if the person threw the ball from their knees way down low, then the ball would have to follow a much higher arch. And in this trajectory, in this pathway, this high angle makes it a little bit easier for the ball to go into the hoop when it stands 10 feet in the air, a certain distance away. And evidently, somebody sat down and performed the calculations using some physics work, and they determined that the height of the basketball, based on the distance away from the player, if we're throwing the ball at an initial 70-degree angle and 3.5 feet above the floor, basically knee height, well, with those parameters in mind, then this is the particular function that determines the height of that basketball. So this is kind of interesting here. The letter x doesn't represent time, as we often see with this h of t function, but it actually means the horizontal distance in front of the person that's thrown the ball. Now, what we need to know here is that the center of the hoop is 10 feet above the floor and 15 feet in front of the foul line. So if somebody's standing at a foul line shooting a free throw, then the hoop is 15 feet away horizontally and it's 10 feet up in the air. So our objective here in part A is to determine the initial velocity with which the ball must be shot in order for the ball to go through the hoop. So if we go back and look at this equation a little bit more closely, you'll notice that it's a function based on the independent variable x, and v is also a parameter in this case, where v stands for velocity. And we get to choose how fast to throw this basketball, essentially, and person who plays the game can practice throwing this ball at a variety of different speeds, and if they can figure out exactly the correct speed or velocity, then it would be almost an assured shot to go in. So on the side of my paper here, I've got a bit of a diagram where I've got an XY axis where x represents x, the distance away from the free throw shooter, y represents the height of the ball. And what we have to recognize is that our goal is to start here at a height of about 3.5 units and to end here at the coordinate 15, 10. We're 15 feet away from the free throw shooter, and we have to have that ball be at exactly 10 feet in the air by the time it reaches this hoop. So we're kind of projecting this this basketball to kind of go in this trajectory right here. So if our goal is to land in this position, which would be the coordinate 15, 10, when x is 15, h of x is equal to 10. The height of the ball is 10 feet above the ground, while the horizontal distance from the shot is 15. Well, we can use that piece of information, or that pair of numbers, if you will, to back substitute into this equation and solve for v. So here we go. In question A, we know that h of x, the height of the ball, is dependent upon this formula. And we're also told very specifically that x has to be 15 feet in front of the the person that shot the ball, and the height of the ball has to be exactly 10 when x is equal to 15. So we can make those substitutions. And there we go. Now, we might be able to reach for a calculator and simplify some of this, especially 2.7 times 15, and adding that value with 3.5. We could also simplify this numerator here too, but I'm not really in an interest, or I don't have any interest in doing that right now. Instead, what I'd like to do is, let's do all of the algebra necessary in order to get v by itself, and then we'll reach for the calculator. So what I see is that I'd like to subtract this term to the left-hand side, and I'd like to subtract this term to the left-hand side. Because again, we're working backwards through the order of operations when we need to solve an equation. So I'm going to do that now. And here again, I'm not reaching for a calculator. I don't want to know what the exact value for this result is, so I'm just going to leave that alone. But what I do want to note is that we now have a value. This will end up being some value over here on the left-hand side. We've got a value equal to a fraction on the right. And I want to remind you that anytime that we need to solve for an unknown variable within a fraction, especially if we've got two fractions that are equal to one another, we can use cross multiplication to solve for that variable. So I know that the product across this diagonal has to be equal to the product across this diagonal. And after multiplying across those diagonals, I can now take one or two more steps to isolate v. We've got this giant term on the right-hand side separated from the v squared by a multiplication sign. So I'll divide both sides by this expression and move it over to the left. And now lastly, to isolate v, we could take the square root of both sides of the equation. Now, since I've done my work with ink that can be erased, I'll just go ahead and erase that square and square root and recognize that this is the expression necessary to calculate v. Now I understand that this procedure is a bit literal for some of you. You're not used to seeing the work done this way. I just want to illustrate to you that this type of question, for as specific as it can get with the decimals and the realistic values, we could solve much of it without the use of a calculator. And only now is the first time that I'm actually going to have to reach for a calculator to get a numerical result. Okay, so I've taken a couple moments to enter this into the calculator. Now, I'll be honest, I forgot to use the square root symbol at the very beginning of this problem, and I instead started writing the fraction first. And so I just wanted to share this with you. On these calculators, we can type SQRT and use a set of parentheses, and anything inside of that set of parentheses will be square rooted. So we'll see when we press enter that symbol will appear, and that's one way to work around fixing your expression without having to retype the whole thing. So if we look closely, we'll see that I'm asking the calculator to find the square root of the exact same fraction that I had written on paper. And if I trust what I had written on paper over here as the correct procedure, then I can trust that the calculated result will be what we're after. So I'll go ahead and press enter, and I see the answer is 30. Now that's kind of interesting that that's precise. Let me just double check the settings here. Sorry, that's in the document settings, so I'm going to press the home button, choose option 5, and then number 2. Yeah, my display digits are set to float, so this will show as many decimals that would come up on the computation. So what I was afraid is that the calculator was rounding our result, but it doesn't look like it is. The end result for this computation is exactly 30, so the velocity is not approximately something, but actually precisely 30. And we do want to note that our units of time, or our units of measure here, were feet, and more importantly, we're told that the velocity is computed, or must be computed, in feet per second. So evidently, with this player, all we have to do is throw the ball at 30 feet per second in this trajectory, and the ball will go through the hoop. Now with our velocity known, we can actually move on to the remaining parts of this question. Part B asks us to write the function for the path using the velocity that we found. Well, that's pretty straightforward. We just rewrite the function as it was given to us, only this time we know that our v value needs to be 30. Now we can actually evaluate this function at 9 as requested in part C. And I can go to the calculator for that. So I'm not going to show the setup here on paper, but on the calculator I do see that this function evaluated at 9 ends up being 15.56. And if you recall how this equation was established, x represented the horizontal distance in front of the player, and y, or h of x, represented the height of the ball. So what that means on this particular graph would be that at an x value of 9, the y value, or the height of the basketball, is about 15.6 units above the ground, or 15.6 feet above the ground. So that would end up being a data point right about here. This question then goes on to ask us to find additional points and graph the path of the basketball. So let's do that. Let's pick some additional points. We don't have to go crazy here, but maybe we'll use 3, maybe 7, and then let's say 12. 3, 7, and 12, and we'll see what those results look like. So you can do what I've just done and copy the equation from above and change the x value to 3, 7, and 12 like we had recommended. Or you can build this function in a graphs page and evaluate the function using the variable command as I showed you last week. But evidently when x is equal to 3, the ball is 10.2 feet in the air. Then when x is, I think I said 8, if I'm not mistaken, or was it 7? I'm going to go with 8 this time. No, I'm sorry, I do want to go back to 7 because I don't want to pick a data point too close to this one. So I'll use 7. Just press the up arrow until the expression is highlighted. Now we can use our left and right arrows to move our cursor. And we'll change every 3, in this case, to 7. So the height here is at about 15 feet. I'll go ahead and round that. And then again, we'll use the number 12. And that height comes out to be 14.14. So 14.14. Graphs are inherently inaccurate, so we're making our best educated guess as far as the position of these data points go. But I think that seems relatively reasonable to think that a ball could follow this particular trajectory as we're throwing it towards the hoop. So again, with this particular example, it's not that I want you to become an expert at basketball or physics, but I do want you to recognize the behavior of this function, how we can interpret and work with it. And if you have concerns or questions on this example, please let me know. I'm going to stop this video here and record another one for the next example.